Hi, we are Team 21, and we are working with NXT Biomedical to create an expandable radial access sheath. My name is Maya, and I'm the team lead, and with me I have Gerald, the marketing lead, Elijah, the business lead, Krish, the creative lead, and Joseph, the prototype lead. Our mentors are Joe Passman, Stan Rowe, and Alex Siegel, all from NXT. I will be starting off by explaining our problem and what we are trying to solve, which is the need for an expandable radial access sheath. Here's the problem statement we are given by our mentors. In short, it explains that there is a need for an expandable sheath specifically for the radial artery that can expand without changing in length and with limited compressive forces on the catheter as it slides through the sheath body. After conducting many physician interviews, we found out that the change in length and the compressive forces are not a big problem during procedures. So we had to change our project a little bit. Now our goal is to create the first ever expandable radial access sheath. For a little bit of background, vascular sheaths in general allow for smooth insertion of devices into an artery. Overall, radial artery access is safer than femoral artery access for quite a few reasons, but the main two being reduced vascular complications such as bleeding and a faster recovery time. As I said earlier, there are currently no expandable radial access sheaths on the market. There are some for the femoral artery, but none for the radial. The need for an expandable sheath is important as it reduces the amount of sheaths that are being inserted and taken out of the patient's body, thus reducing the chances of complications such as spasms, and decreasing waste. Our device combines the best of both worlds, a safer procedure in the radial artery. Next, I will be passing it off to Joseph to talk about our design.
Thank you, Maya. So here is our current design prototype. On top, we have our sheath, which is handmade, cut, and glued together. And then on the bottom, we have our 3D printed hub along with the tubing and side-on stopcock. Next slide, please. So how our sheath design works is that it is made up of two different materials that alternate between a rigid and elastic material. The rigid part of the sheath eliminates the problem of length change by keeping its length at a fixed position, while the elastic part of the sheath allows it to radially expand. Next slide, please. We will then also add a hydrophilic coating on the inside to help reduce the problem with friction between the sheath and the catheter. Next slide. And here is just a CAD model of our hub that goes along with the sheath. We've also made our own cap and hemostasis valve that goes with the hub, and then you can attach the tubing and the sheath to it as well. Now we'll go on to Gerald to talk about our design inputs and outputs.
Thank you, Joseph. Our sheaths should offer the same features as other sheaths on the market, with prevention of bleeding out and ease of use for doctors being our main focuses. Next slide. Due to our prototyping restrictions, we are actually unable to prototype the small 4 French starting diameter that we had initially started with. So our minimally viable product, we went up to a 6 to 9 French size change, keeping the same 3 French total increased as promised before. Next slide, please. Our primary validation and verification tests revolve around the device itself. As mentioned before, we are testing for a 3 French increase and return, and for any increase in the sheath length. The resistance of the tools being pushed through the sheath is also being tested with and without Surgilube, which is our lubricant of choice. And we have a bleeding control test to ensure that our device does not leak at any major failure point. Next slide, please. Our tests and results are listed in this table. We found that the sheath was able to accommodate our minimum size introducer, and using Surgilube, we were able to easily account for the 9 French size introducer. The sheath was also able to shrink back into the 6 French size with relative ease. The sheath showed less than a 1 millimeter change in length, making it negligible. And for the bleeding control test, tap water was injected into the sheath while we observed for major failure points in the sheath and the hub. In these tests, we successfully verified that our prototype meets our minimally viable product requirements. Next slide, please. The only validations we were unable to get to testing were for compression, for radiopacity, or the ability for the sheath to be seen under imaging, and for biocompatibility with humans. These tests are not currently within our scope of verification, but they are planned for the future. I will now pass it on to Elijah, who will talk about our failure modes analysis.
Thank you, Gerald. So let's take a look at our failure modes. Next slide. To start with, our team researched different recalls to see how our device could fail. From these, we saw 4 major failure points for similar devices. For example, there could be leakage occurring during use. There can be an increase of bleeding from the site that is inserted. Equipment could not be compatible with the sheath itself, or in some extreme cases, parts of the sheath would break during use. So from this information, we were able to make an FMEA chart that analyzes all of these failure modes. Next slide. This chart itself gives an in-depth way for how and why these failure modes occur, but we want to highlight how we plan to prevent these occurrences. So to make it simpler, we outlined the 4 failure modes we wanted to focus on preventing the most in the table on this slide. So for valve leakage, we performed strict testing of both the capabilities of different silicons and their compatibility with the equipment. To prevent an increase of bleeding, a hydrophilic coating could be added to reduce friction, but the overall smaller size of our sheath will also help with that. As for equipment not being compatible with the sheath, the fact that our sheath will be able to expand through French sizes pretty much solves that problem itself. And finally, to ensure that there's no breakage happening during use, we've done strict material testing to ensure that the sheath will deform rather than breaking when too much force is exerted on it. Now we'll pass it over to Krish to talk about our next steps.
Thank you, Elijah. Next slide, please. While the main tests for functionality included 3 French expansion and checking for fluid leakage, there are other tests which are necessary to accomplish. Further device testing includes a stress strain test to ensure the sheath does not deform under load, as well as a pressure test to assess how the sheath functions under the internal pressure of blood. A wear test is needed to ensure the period a sheath can withstand deterioration of material, as any would be dangerous for the patient. Adding to this, biocompatibility would evaluate whether or not the sheath causes skin irritation or any allergic bodily reaction. Lastly, the sheath must be visible under imaging like X-ray and ultrasound. Next slide, please. In terms of manufacturing, multi-material printing is currently the next step for our prototype, as the design focuses on the binding of 2 materials. Additionally, we are looking at other methods to build, such as extrusion as well. Since this is all still part of the prototype stage, advancing requires a consistent and accurate manufacturing method that meets all design and acceptance criteria. Next slide, please. To close, we would like to thank the following people for their assistance: Dr. King, Dr. Kine, and our industry mentors, Joe and Alex. Here are references, and thank you so much for listening.